Good afternoon from Vienna. My name is Martin Reggie, and I am an Associate Program Officer at UNODC's CBRN Terrorism Prevention Program of the Terrorism Prevention Branch. I am delighted to welcome participants to today's webinar, the fifth in a series of 10 on key aspects of the International Convention for the Suppression of Acts of Nuclear Terrorism, or ICSANT. I would like to convey UNODC's gratitude to the European Union for enabling this important activity and for its crucial contribution to the promotion of ICSANT through the EU-funded project on Union support for the universalization and effective implementation of ICSANT. ICSANT is an essential tool for preventing nuclear and radiological terrorism and improving nuclear security worldwide. It contains essential provisions dealing with international cooperation in criminal matters related to the offenses it establishes. ICSANT can benefit all states parties by facilitating international cooperation, including the exchange of information on radiological and nuclear terrorism, threats, related investigations, and prosecution or extradition. Today's webinar focuses on the discipline of nuclear forensics through a related case study. UNODC, through its CBRN programming funded by Canada and the European Union, assists member states by building the capacity of criminal justice officials with regards to ICSANT. Nuclear forensics is a key tool when it comes to investigating and prosecuting criminal conduct involving radioactive material. ICSANT and the material it covers present particularities in relation to criminal proceedings, inter alia with regard to investigations, evidence gathering, preservation and admissibility, and international cooperation. Soon, you will hear from Mr. Gary Epic, a nuclear security officer in the Division of Nuclear Security at the International Atomic Energy Agency, or the IAEA. We are grateful to him and to the IAEA for their contribution to this event. But before that, let me begin by providing you with a brief primer on ICSANT. A short historical background on ICSANT. Negotiations were called to address gaps in the international legal framework for preventing and responding to acts of nuclear terrorism. As such, ICSANT was drafted by an ad hoc committee established by the UN General Assembly in 1996. The convention was adopted by the General Assembly in April 2005 and opened for signature in September 2005. It entered into force on 7th of July 2007, and the depository is the UN Secretary General. ICSANT is one of the 19 international legal instruments against terrorism. It follows a similar structure to those other counterterrorism instruments, including the criminalization of certain acts, instances of mandatory and optional jurisdiction, the principle of extradite or prosecute, or aut dedere or aut judicare, where a state party must extradite an alleged offender to another state party or undertake a prosecution themselves. And lastly, certain mechanisms to facilitate international cooperation. In terms of the scope of ICSANT, the type of material covered is included under Article 1, which lists definitions for radioactive material, among other things. Radioactive material means nuclear material and other radioactive substances which contain nuclides which undergo spontaneous disintegration and which may, owing to their radiological or fissile properties, cause death, serious bodily injury, or substantial damage to property or to the environment. And you'll find the definition for nuclear material listed there as well. Article 2 sets forth the offenses that are criminalized. Specifically, ICSANT establishes offenses involving radioactive material, radioactive devices, or nuclear facilities where they've been committed unlawfully, that is, in the absence of a legitimate justification, and intentionally, that is, deliberately. These offenses range from illicit possession or use of nuclear or other radioactive material or radioactive devices to damage to nuclear facilities, and include also a series of ancillary offenses. The list of offenses to be criminalized pursuant to this convention, again, is found in Article 2, and it's always important to know that for an offense to fall under ICSANT, it needs to be committed with a specific intent. Those include the intent to cause death, serious bodily injury, or substantial damage to property or to the environment, or the intent to compel a natural or legal person, an international organization, or state to do or refrain from doing an act. This is the so-called terrorist intent. ICSANT also includes different mechanisms to facilitate international cooperation, which you'll see listed on screen. Those first two you'll find covered in some of our previous webinars, so I would encourage you to check those out as well. Some of the assistance you will hear about today may fall under Article 14, which calls for states parties to afford one another the greatest measure of assistance in connection with investigations or criminal or extradition proceedings, brought in respect of the offenses set forth in Article 2, including assistance in obtaining evidence at their disposal necessary for the proceedings. I encourage you to please visit our UNODC ICSANT website, where you'll find a repository of all the resources we've developed, including recordings of the previous webinars. It's available in all 6 UN official languages and regularly updated. And lastly, I'll just highlight some of the manuals and technical assistance tools that we've developed, which may be of use to participants. Those are, again, all available through our UNODC ICSANT website. And that's the end of our brief primer on ICSANT. You'll soon hear from Gary, but while he presents, if there's any questions that come up, we have a dedicated question and answer session. So please send those questions to the second email listed on screen, unodc-icsant@un.org. I'm pleased to welcome Mr. Gary Epic, a nuclear security officer in the Division of Nuclear Security at the IAEA. He's currently acting as the technical coordinator of the IAEA's program of member state assistance in the areas of nuclear forensics and radiological crime scene management. An isotope geochemist and mass spectrometrist, he was previously a staff scientist at Lawrence Livermore National Laboratory in the United States of America from 2010 to 2017. From 2017 through 2019, he worked as a mass spectrometry specialist at the IAEA's Safeguards Laboratory in Seibersdorf, Austria, supporting the environmental sampling program. From 2017 through 2019, he supported the nuclear forensics program of the United States Department of Energy's Office of Nuclear Smuggling, Detection, and Deterrence in Washington, D.C. He's the author of several articles on nuclear forensics, nuclear safeguards, and isotope geochemistry. Again, following Mr. Epic's presentation, we will have a brief Q&A session. So please email those questions to unodc-icsant@un.org, and we will attempt to answer them during the allocated time if available. Gary, the floor is yours.
Thank you so very much, Martin. And I'd like to thank UNODC for providing us, myself, this opportunity to speak on behalf of the IAEA about nuclear forensics and how it relates to the good work of UNODC and ICSANT. If you'll give me 1 second, I will present my slides, and please let me know if they do not appear. Can you see that?
Yep, we can see them.
Okay, great. Let's get started. So, here we go. Okay, so for my presentation today, I've broken out into 3 parts. First, I will set the stage a little bit by talking about the role of nuclear forensics, specifically when it comes to nuclear and other radioactive material encountered out of regulatory control. In the second part of my presentation, I will talk specifically about the IAEA's role in assisting member states in the development of nuclear forensics. And then finally, I'll try to put all the pieces together in the context of, I think, a very interesting case study that involved the nuclear forensic examination of uranium that was actually discovered during a drug raid. So that's what we'll talk about today. So for part 1, nuclear and other radioactive material out of regulatory control and the role of nuclear forensics. So this is probably not new information to anybody on this webinar, but nuclear and other radioactive material out of regulatory control can be used to cause harm. And I think it's important to kind of set the stage for why we care about this and why we're doing what we're doing to assist states in developing nuclear forensics. And that's to combat these 2 potential threats. There is the radiological dispersal device pathway to creating a weapon that can cause people harm. This is sometimes referred to as a dirty bomb. This type of device can be constructed using either nuclear, but more likely to be using radioactive material, following the definition that Martin described earlier in his presentation. It's important to note that a device like this would not generate nuclear yield. This would be a mechanism for distributing radionuclides into the environment, which could have a significant effect, causing fear, panic, loss of life, and damage to health among the population affected by such an incident. And then the second pathway, the almost unthinkable pathway, which is the improvised nuclear device. It's important to note that an improvised nuclear device can only be constructed using special nuclear material, namely highly enriched uranium and plutonium. This would, of course, generate some amount of nuclear yield, and it's almost incomprehensible to imagine the damage that such an incident would cause to life and health of the affected population. So this is what we're trying to combat. This is what we're all working towards preventing. So a little bit about the consequence versus likelihood of various types of material out of regulatory control. So the plot I have on the left here is a plot with axes but no units, because it's meant to be really qualitative, looking at the likelihood of an incident using a particular type of material and the consequences that would have if that material were to be weaponized. So as I think most people would agree that the weaponization and the creation of an improvised nuclear device is an unlikely occurrence, but the consequence would be extremely high. And that, in contrast, the use of other types of nuclear material that are not weaponizable for an improvised nuclear device, such as low-enriched uranium or yellow-cake uranium, those materials are more accessible, but the effect that would have on human life and health would be significantly lower. And then somewhere in the middle, and I think reasonable minds could disagree on where that would belong, would be the radiological dispersal device using a high activity radiological source, like a cobalt-60 source stolen from a hospital, for example. That would certainly have a major effect. Here on the right, I have some data from the IAEA's Incident and Trafficking Database, the most recent fact sheet released in 2024. So up to between the period 1993 and 2023, there have been 4,243 confirmed incidents of nuclear and other radioactive material out of regulatory control. And 350 of those incidents are or likely to be connected with trafficking or malicious use. Of the total number, the 4243 number, approximately 14% of those incidents involve nuclear material, and approximately 59% of those incidents involve radioactive material. And I use these data are important because they show the scope of the problem, that these incidents, they do happen with some frequency all over the world. And these are just the incidents that we have knowledge of because of data tracking in the ITDB. Surely this is a global minimum, and actually there are more incidents which are unknown, which have occurred. And it's also, especially with the cases which are likely or are connected with trafficking or malicious use, those are all cases where an investigation or an examination of the nuclear or radioactive material would very likely occur. So each of these could be a nuclear forensic examination, and many cases that aren't linked to smuggling and trafficking also could be subjected to nuclear forensic examination should a state decide to pursue that pathway. So nuclear forensics is actually a widely used tool all around the world. Here are some notable cases of uranium out of regulatory control that have occurred in Europe. So what you're looking at here, the x-axis is just a timeline between 1990 and 2010. And the y-axis is the percent enrichment of the uranium that was seized or encountered out of regulatory control. And the symbols, the smaller symbols, would be cases where there was less than 1 kilogram of material seized, and the larger symbols are cases where there was more than 1 kilogram of material seized. So you can see that from 1990 to this period to 2010, that these incidents actually occurred with a relative frequency in Europe. There were also 2 plutonium incidents that occurred in 1994, but I want to highlight 2 particular incidents in, let's say, country A and country B. These are materials which are highly enriched uranium and look very similar to each other, but they actually were encountered in 2 different countries. So one of the things nuclear forensics can enable us to do is to link cases, to compare materials, to say, is material from country A, which you can see at the top image, dissimilar to material found in country B, which according to these photographs actually looks quite similar, and it turns out that they are quite similar. So questions that might be asked are these materials or cases linked, and how would we even know if they were? So when incidents like this occur, states want to be able to do two things. The first thing that states want to be able to do are investigate incidents of nuclear or radioactive material out of regulatory control and use the output of that investigation to prosecute criminal smugglers and traffickers. So use these data in a court of law. And the other thing states want to do is they want to understand the origin of these materials out of regulatory control when they're encountered within their borders. Is this a domestic material, or does this material look like it may have come from outside of a particular state? These are questions which states want to answer. And the way that which most states go about doing this, at least a major contributing factor, is nuclear forensics. I believe most everyone on this call is familiar with nuclear forensics, but I want to provide the IAEA's official definition of nuclear forensics just to constrain what we're talking about here. So according to IAEA Nuclear Security Series 2G, nuclear forensics is the examination of nuclear or other radioactive material or evidence that is contaminated with radionuclides in the context of legal proceedings under international or national law related to nuclear security. Nuclear security is the prevention and detection of and response to criminal or intentional unauthorized acts involving or directed at nuclear material, other radioactive material, associated facilities, or associated activities. And the IAEA's Division of Nuclear Security is involved at every step of this pursuit, from prevention, detection, and response, which I show here on the bottom of this slide. But what we'll be talking about in this presentation for the rest of the presentation is nuclear forensics, which falls kind of towards the end at the response phase. So we're talking about the analysis of evidence, the attribution of this material to an origin potentially, or the use of it in a court of law, in criminal proceedings. So basically doing science to determine what are we looking at? What is this material? Could be many things, and nuclear forensics is the key tool to enable us and enables many states to make this determination. And as I mentioned, states want to do two things with nuclear forensic evidence. They want to assist states in criminal investigations, or states want to use nuclear forensics to assist in criminal investigations of nuclear security events. Nuclear forensic data can and has been used in criminal proceedings, and the purpose of these data and the use of these data is to, among other questions, would be to answer the question, is the possession of this item a criminal act? Is this in fact enriched uranium? How do we make that determination? Is the enrichment of that uranium exceeding whatever the legal statute may say is illegal to possess outside of regulatory control? And then number two, states use nuclear forensics to aid identification of the origin of nuclear and other radioactive material encountered out of regulatory control. So states can use nuclear forensic data, the physical, chemical, elemental, and isotopic properties, the signatures of these materials, to determine whether they belong in the state's nuclear material holdings or radioactive material holdings and escape regulatory control from within the state, or perhaps is inconsistent with an origin from within the state and therefore must be a cross-border smuggling issue. So nuclear forensics can be then used for a state to answer the question, is this material out of regulatory control? Is this ours? Did it fall out of regulatory control from one of our facilities, from one of our laboratories, from one of our hospitals or industrial facilities? Okay, so now I want to talk a little bit about the IAEA's specific role in assisting member states in the development of nuclear forensics. I think this is probably a history which is well known to most people on this webinar, but nuclear forensics was established in the early to mid 1990s. You saw the plot a few slides ago where I showed some notable instances of uranium out of regulatory control in Europe. This was around the time it was noted there was a significant increase in the reporting of nuclear and radioactive material out of regulatory control. This observation was considered to indicate an increase in illicit trafficking of these materials, so loss from state possession to possession by non-state actors. So in order to investigate such incidents, national authorities requested from the scientific community information about the physical, chemical, elemental, and isotopic properties, the composition, the nuclear forensic signatures of the material itself. This was an area where nuclear materials scientists, material scientists, and geochemists and physicists had a lot of experience with, but had not been applying to material outside of regulatory control up until this point. And what national authorities wanted to know was the how, when, and where these materials were produced, and how they their histories outside of regulatory control. I want to make one thing very clear, which is that the IEA, we assist member states in developing the capabilities to perform nuclear forensic examinations, but we do not perform them ourselves. The IEA is not and is never engaged with casework, so please do not send us your samples. Nuclear security is the responsibility of the state, and states would like to, and many states are working on developing national nuclear forensic capabilities to perform these analyses, perform these examinations themselves. So what we do, we endeavor to assist member states in the building of national capacity in nuclear forensics. So I currently work for the Crime Scene and Nuclear Forensics Unit in the Division of Nuclear Security here at the IEA. And me and my team, our goal as a group is to ensure that states have a nuclear forensic and radiological crime scene management capability commensurate with their nuclear security needs and requirements. Now, it's important to note that not all states' needs and requirements are identical. Some states may require a more advanced nuclear forensic capability or a more capable set of analytical techniques, and some states may require less depending on their nuclear material holdings, depending on knowledge of cross-border smuggling incidents and other factors as well. And then in terms of how we achieve this goal, we assist states in developing and sustaining the technical and associated capabilities necessary to perform radiological crime scene management and nuclear forensic examinations in support of investigations into criminal or intentional, unauthorized, or suspected acts involving nuclear or other radioactive material. We also work to develop nuclear forensics and radiological crime scene management nationally, regionally, and globally through collaboration with member states and other international organizations engaged in capacity building in this area. This would be a good example of the collaborative work that UNODC and the IEA are doing in nuclear forensics. And the figure you can see in the lower left talks a little bit about how we accomplish these goals. You can break it down into sort of 4 quadrants of the program. The first would be training courses and workshops. The second is publications. The third would be research and development through coordinated research projects, or CRPs. And then finally, a fourth catch-all for new initiatives that don't fit neatly into any of those 3 categories. And I'll talk a little bit about some examples of each of those components of the program in just a minute. So our program started roughly in 2005, 2006. And since 2006, we've established a mature nuclear forensics support program. We've conducted over 50 training courses and workshops in nuclear forensics, and over 30 states have participated in nuclear forensics-focused coordinated research projects. We actually just launched the 4th CRP in nuclear forensics last year, and we have the largest amount of participation yet in this CRP. We've also published several tech docs, and of course the Nuclear Security Series 2G, which was referenced earlier. Most recently, we published a tech doc called IEA Tech Doc 2019, which talks about the many different analytical techniques which can be applied to a nuclear forensic examination by states. So I highly recommend taking a look at that publication if you haven't already done so. A brief history of our program. I won't go into too much detail here, but I just want to show sort of the breadth of activities that our effort here has undertaken since 2006. So we published the first implementing guide in 2006, and that guide has been revised in 2015. We've also published key tech docs in area of National Nuclear Forensic Libraries in 2018. That's TDL 009. You can see that with the sort of maroon red arrows on the figure on your screen. And then I mentioned IEA Tech Doc 2019, which was published about 2 years ago. We've also launched 4 CRPs. The 4th was launched last year, and is currently ongoing with over 20 states participating. I think the number is actually quite a bit higher now. So we have a lot of interest in participating in research and development. And we also have a set of training courses and workshops. I'll talk a little bit about some of those, but we launched the Nuclear Forensics Methodologies course and the Basic Introduction to Nuclear Forensics course in 2012, followed by the Practical Introduction to Nuclear Forensics course in 2013. And I'd like to highlight that we actually launched 2 brand new workshops in nuclear forensics and radiological crime scene management this year. I'll talk a little bit more about them in a forthcoming slide. And we've also had 2 technical meetings and 1 international conference on nuclear forensics over this time period. So in terms of training courses and workshops, I think many people are familiar with our program, but in case you're not, the way to look at this figure is on the right side is the nuclear forensics focused training courses and workshops that we have. And then on the left side is the radiological crime scene management training courses and workshops. So we recently launched the integrated workshop on radiological crime scene management in nuclear forensics. That takes place at the recently opened Nuclear Security Training and Demonstration Center in Seibersdorf, Austria. We also have the Basic Introduction to Nuclear Forensics course, which is a bit of a traveling roadshow. We do that at the regional or international level at member states all around the world. We offer the Practical Introduction to Nuclear Forensics, which is a 1-week hands-on practical course and actual analytical experiences in the laboratory, primarily in the laboratory. That course is hosted by Hungary, Australia, and most recently France. And very much thanks to our French colleagues for developing a French language version of that course for the very first time. We also recently launched the peer-to-peer workshop in nuclear forensics, which was debuted in August of this year. I'll talk a little bit more about that in about 2 slides. And then finally, sort of the capstone of our program is the Nuclear Forensics Methodologies training course, which is a 2-week hands-on practical course, which covers virtually every key analytical technique used in nuclear forensics by member states. Everything from gamma spectrometry to mass spectrometry, alpha spectrometry, X-ray techniques, and many others, including the associated sample handling and chemical separation techniques, which are required for some of these analytical techniques. And that course is offered in the United States at Pacific Northwest National Laboratory, and in Germany through the European Commission at the Joint Research Center in Karlsruhe, which actually just concluded just a few weeks ago. So just a little bit more about our new offerings. I could probably spend this entire webinar talking about our training program, but I just want to highlight some of the new offerings because I think that might be most relevant to many people on this call. I mentioned the integrated workshop on radiological crime scene management in nuclear forensics. This is a workshop that gives participants the opportunity to conduct hands-on exercises from initial discovery of material out of regulatory control, collection as evidence, management of radiological crime scene, and then subsequent nuclear forensic examination. This course is designed to take advantage of the unique capabilities of the NSTDC in Seibersdorf, Austria, giving participants a thorough introduction to both RCSM and nuclear forensics. One of the real benefits of this is you get in-field responders working with laboratory scientists together so that we can see so that laboratory scientists can see how the in-field responders work and handle problems and vice versa. So we can all learn from each other. So we had 2 offerings of this workshop in this year, and we plan for 3 in 2025. And then the peer-to-peer workshop in nuclear forensics, which we launched in August in Indonesia, focusing on the ASEAN region. This course is really designed for member states and for individuals who've had training courses and workshops in nuclear forensics before and have some technical experience in this area. So they have an opportunity to apply their experiences and their knowledge, working with technical personnel from other member states in their region. So we constructed the workshop around several topics, including the handling of mock radioactive materials, gamma spectrometry, scanning electron microscopy, and mass spectrometry. And then there's a capstone exercise on the final day, which takes advantage of all of the learning that went into the first 4 days and applying it to a new scenario. You can see on the figure on the photograph on the bottom left of this slide, this is 3 participants in the workshop examining some scanning electron micrographs and comparing and contrasting the physical nuclear forensic signatures that they can observe, and going from and being as descriptive as possible and drawing conclusions based on their observations. So this workshop is full of interactive exercises like that. And of course, it's facilitated by us and international experts, but really this workshop truly thrives when you have enthusiastic and experienced personnel, which we were very fortunate to have in the debut offering. And we look forward to offering this in approximately once per year in different regions around the world. I spoke a bit about publications. I won't go into too much detail here other than to highlight the Nuclear Security Series number 2G, Rev 1, Nuclear Forensics in Support of Investigations. If you've never consulted this implementing guide, I highly encourage it. You can find it for free on the IEA website. This is sort of our North Star of our program, and we use this to design our member state program of member state assistance. In terms of other publications, I mentioned IEA Tech Doc 2019, which is, I guess it's not so new anymore, but it's our newest publication, which focuses on analytical techniques and focuses on 19 different analytical techniques and goes into considerable detail about how these techniques have been applied to nuclear forensics by states all over the world. We also have information published from technical meetings, such as a technical meeting in 2022, and we will look forward to launching or publishing a new tech doc on the technical meeting, which happened in 2022, just hopefully early next year is what we're aiming for. We also published the results of coordinated research projects, and we look forward to publishing the outcomes of the most recently concluded CRP sometime in 2025. A little bit more about CRPs. So the current CRP is called Nuclear Forensic Science to Bridge the Radiological Crime Scene to the Nuclear Forensics Laboratory. We launched this last year. We identified 12 specific objectives or 12 topics that we encourage member states to submit proposals to. You can see them in the hexagons on the left of the slide. And we're very excited that this CRP is fully up and running, and states have received financial support and are actively undergoing and performing research and development in interesting and key areas in nuclear forensics. So I could spend probably the rest of this presentation just talking about the other things that the IEA does to support member states, but I think it's probably more beneficial and more interesting if I can put it in the context of a case study. So I am going to spend the rest of this presentation talking about a fascinating case study, which I think illustrates many of the principles that I've talked about in the previous slides, and I'll try to interject where the IEA can support member states in developing capabilities like the ones you'll see illustrated or demonstrated in this case study. I'd also like to thank our colleagues in Australia who gave us permission to discuss this case study because this is an incident which occurred in Australia. Everything you'll see has been openly published and released, so there's nothing sensitive remotely about this material, but I just want to acknowledge the hard work done by the Australian Nuclear Science and Technology Organization, from which the vast majority of these data originate. But a little bit about the case study itself. So on April 1st, 2009, in Melbourne, Australia, police were performing a raid of a drug manufacturing, illegal drug manufacturing facility, and they encountered some strange, seemingly radioactive material that looked a bit like this. So here are two photographs of the material that they found. Both materials were radioactive. One is sort of orangey, yellowy powder, depending on your perspective. And the other one is sort of dark green to gray powder. Uranium materials, as you'll see that they are, radioactive materials in an illegal drug lab, a bit of a strange thing to encounter. So that caused the Australian Parliament to initiate an inquiry. And one of the really interesting things about this case study is it gives us an opportunity to illustrate the way in which nuclear forensics is used to answer and address specific questions posed by authorities in a member state, in this case, the Australian Parliament. So what you see on the left of this slide are six of a larger number of specific questions that the Parliament wanted answered about this specific case. I won't go through all of them, but I do want to highlight the ones that are bolded in red, because those are questions which nuclear forensics can provide some insight on. So in inquiry question number 3, they wanted to know what the chemical form of the uranium was and its isotopic composition. Number 4, they wanted to know where the uranium was mined and last chemically processed, and whether it can be determined if this uranium came from an Australian uranium mine, of which there are several. Australia is a very important and significant producer of uranium in the form of uranium ore concentrate, which is naturally occurring uranium that's been mined and milled, so the uranium is concentrated. For number 5, they wanted to know if the uranium was in fact Australian, could it be linked to a specific existing mine or a facility in Australia, such as the ANSTO itself or other facilities within Australia. And number 6, they wanted to know if the material is similar to the material or related to the material which was lost during a security breach at the Olympic Dam mine in 2007, where 10 300-gram jars of yellowcake were encountered out of regulatory control. So the good thing about this is nuclear forensics can provide some insight to all of these questions here. So what happened next was the materials ended up in the hands of the nuclear forensic scientists at ANSTO, and they shared some of the sample with Lawrence Livermore National Laboratory, which is located in the United States of America. Upon completion of this nuclear forensic examination, the results were published in this publication, which you can see on the lower left of the slide, Nuclear Forensic Analysis of Uranium Oxide Powders Interdicted in Victoria, Australia. So I highly encourage you, if you're interested in knowing more about this case study, to consult this publication. Please feel free to email me if you cannot find it. I'd be happy to share it. In terms of the investigation itself, I've already mentioned the yellow powder and the dark green powder, but there are also 2 other interesting discoveries made alongside the uranium powder. One is that a dead moth was associated with the yellow powder. So they found this dead moth in the powder, which is an unexpected discovery, but also one that could potentially provide insight on where this material came from. And then in a different sample, they also found a staple, which you can see images of on the slide there. So in addition to interrogating the powders, the teams also looked at the moth and the staple to see if there was information that could provide some insight on origin of this material. So there are a number of analytical techniques which could be applied to materials like this. I won't mention all of them, but this comes directly from IEA Nuclear Security Series 2G. Many laboratories choose to segment their analytical approach into the first 24 hours, the first 1 week, and the first 2 months upon receipt of the sample. And there are quite a few analyses which can be performed within 24 hours of receipt of the sample. That would include initial sample unpacking and handling, and then photography and optical microscopy, basically recording the physical state of the material upon arrival. Whole gamma spectrometry, taking gamma spectrometry measurements of the sample, as well as X-ray fluorescence spectrometry, which can reveal the elemental composition of the sample. Within 1 week, whole gamma, long count gamma spectrometry, so taking a long measurement of the materials, as well as techniques like quadrupole inductively coupled plasma mass spectrometry, which I'll talk a little bit about if this is a technique you're not familiar with, X-ray diffraction, which can reveal the chemical form of the uranium compounds present in the sample, and scanning electron microscopy, which can be used for determination of the physical properties and the elemental properties of the material. And then within 2 months, more advanced analytical techniques can be applied. I won't go through all of them here, but I will specifically talk about the 6 that I've highlighted here. So gamma spectrometry, quadrupole ICP-MS, X-ray diffraction, scanning electron microscopy, multi-collector ICP-MS, and then examination of the moth and the staple. For the people on this webinar who may not be familiar with these analytical techniques, please don't worry. I will try to explain the bare minimum that you need to know to understand these data and why these techniques were used. But first, I'll talk a little bit about the gamma spectrometry results. So what you see on the left of the slide here is a 3 isotope plot So the x-axis is the 235-238 uranium ratio of the yellow powder and the dark green powder, and the y-axis is the uranium-234, uranium-238 isotope ratio. If that's all new to you, don't worry. The most important thing to note here is there are two things. That uranium-235-238 ratio is a measure of enrichment, and both of these samples are significantly depleted in 235 relative to 238. I don't have natural uranium plotted on this plot because it would be far off to the right. You wouldn't even be able to see it on the plot. The other thing to note is that the two samples seem to have distinct isotopic compositions, and certainly in terms of their 235-238 ratio. So you can see that they don't overlap on the x-axis, even if they overlap on the y-axis. The error bars are there, so you can see that for yourself. Both samples also have unique and different uranium concentrations. So that's the amount of total uranium per gram of sample. The yellow powder had about 0.69 grams of uranium per gram sample, and the dark green powder was more concentrated in uranium at 0.75 grams per gram. This was determined using an electrochemical titration technique called the Davies-Gray technique. Some information about gamma spec, but I think most people on this webinar are familiar with gamma spectrometry as applied to other areas if you're not familiar with how it's used in nuclear forensics. So what questions were we able to answer with this? So the Parliament wanted to know what's the isotopic composition? Well, we already have some information here. So both powders are depleted uranium, clearly, well outside of uncertainty of the measurement. And then inquiry 4A, did this come from an Australian mine? Well, Australian mines, as all uranium mines do, produce uranium of natural isotopic composition, and these materials are clearly depleted. So that would suggest that they do not have, they're not similar to, are not consistent with the type of uranium produced in Australian mines. So the next technique that we'll talk about is quadrupole ICP-MS. I know that's kind of a bit of an alphabet soup of letters. So if you're not familiar with this technique, it's a destructive analytical technique. So we must dissolve some amount of the sample in order to perform this measurement. And this allows us to get actually pretty high precision data for virtually every element on the periodic table, although the elements that were measured in this study, I've highlighted in red on this periodic table you can see in the middle of the slide. One of the great things about this analytical technique are the detection limits are really, really low. So for some elements, the detection limits can be as low as 1 part per trillion, although for most elements, it's a bit higher than that. The typical analytical run can take about a day, longer with sample preparation. So can't go through all of the trace element data that we could, but there's a couple notable results. Probably the most notable is the potassium content of the yellow powder was 6.7 weight percent. So in addition to being a uranium material, there's a significant amount of potassium in this material. There was also a much lower but significant amount of iron in this material. Most elements that we measured were above the detection limit, the instrumental detection limit. So there was a lot of impurity. This yellow powder was quite impure, whereas the dark green powder had much lower abundances of trace elements. Potassium was below detection limit, below 100 ppm, and iron, magnesium, and lead were the most notable trace elements of higher concentrations. So what does it tell us about the chemical form? Both powders have significant abundances of various elemental impurities, and the yellow powder seems to be some kind of potassium-rich uranium material. So again, these materials seem to be different from each other and don't seem to be consistent with an origin from Australian mines. X-ray diffraction is a technique. This is a non-destructive analytical technique which allows us to determine the chemical form of the crystalline phases that are present in the sample. Typical analytical run for this type of measurement will take typically a few hours, maybe 2 to 4 hours. When I say chemical form, what I mean is the chemical forms you see on the slide in front of you. X-ray diffraction allows us to make a determination of what this chemical form is. So although it was not an exact match for the yellow powder, the closest match was a potassium uranium oxide with hydrated K2UO2 with 4 H2O molecules. Not an exact match, but that was the closest match. So some kind of unusual uranium potassium material and contrasted significantly from the dark green powder, which was UO3 plus 2H2O. There were several minor phases present in the dark green powder. But the important thing to note is this is all consistent with the previous measurements, that this yellow powder is some kind of unusual potassium-rich oxide uranium compound, and the dark green powder is a more common UO3 compound. So again, we're building a better understanding of these materials the more and more varied analytical techniques we apply. So we're getting a lot of insight as to what these materials might actually be and whether they originate from Australian mines, which is really looking like they don't. Okay, so the next analytical technique I want to talk about is scanning electron microscopy. This is a non-destructive analytical technique. However, your sample is loaded into a sample chamber under vacuum, so ensuring that the sample does not get loose, particularly if it's a powder sample, is actually quite a challenge because you don't want to contaminate your scanning electron microscope with radioactive material. It allows us to get these amazing submicron resolution images that you see on the bottom left of your screen. Many SEMs have a mechanism by which you can determine the elemental composition of specific points on your material. Won't really talk about that, but that's an important capability of this analytical technique. And you could spend a few hours or a few days or a lifetime if you want to collect images and perform measurements as you search around on your sample. On your screen, you see a few example scanning electron micrographs of the yellow powder on the left and the dark green powder on the right. And if you contrast the scanning electron micrographs on the left to the ones on the right, you can see some pretty clear textural and physical differences between these two materials. On the left, it looks more kind of blocky and more coarse-grained. On the right, we're looking at a more fine-grained type of powder with sort of subangular grains at the 5 to 10 micron scale. So talking about its chemical form, it looks like these two samples have distinct particle morphologies, and that the yellow powder consists of larger particles than the dark green powder. So again, we're gaining more and more information about these materials. Okay, now I'm going to talk about multi-collector ICP-MS analyses, which is gives us a very similar data set to what you saw previously on gamma spectrometry. So if you look at this, I just went back a few slides. So if you look at this one, you see the uncertainties here, the error bars are relatively speaking quite large. Form a similar measurement using a completely different analytical technique. So in the on the plot on the left, you see it's the exact same plot. You have the 235, 238 versus 234, 238 on the y-axis. Here I plotted the isotopic composition of natural uranium. It's that big X in the upper right-hand corner, and the yellow powder and the dark green powder. There's no uncertainties plotted here because the uncertainties are so small that you just can't see them over the size of the symbols themselves. So this is an extremely precise analytical technique for performing isotope ratio analyses, and particularly useful for uranium and plutonium materials. So that's the benefit of using a multi-collector type of instrument. Don't worry about if you're not familiar with the different types of mass spectrometers, but this is an optimal one for isotope ratio measurements. So what we see here is consistent with the gamma spec data, but is actually more precise and allows us to determine that not only does the 235, 238 ratio differ, but the 234, 238 ratio is distinct between these two materials. And these materials are significantly depleted relative to natural uranium. On the right, one additional benefit of this technique is it allows us to measure the isotope uranium-236, which you can see on the y-axis on the right plot. So the uranium-236 is indicative of, in uranium materials, is indicative of irradiation. So natural uranium pulled from the earth, mined and milled, contains effectively no uranium-236. But as you can see here, these two materials contain a significant, well above the detection limit amount of uranium-236. The only way this could occur is if these materials are somehow associated with irradiation in some kind of nuclear reactor. So these are irradiated, likely reprocessed materials. So again, all of this is pointing to that these materials do not look like the kinds of materials that would come from Australian mines. In terms of its isotopic composition, again, we confirm here that it's depleted, and almost certainly irradiated at some point to generate the uranium-236 we see. And then finally, examination of the moth and the staple. So with the moth, the hope was that we could determine its origin based on a determination of its genus and species, thinking that moths, different types of moths would occur in different regions, and if it's possible to geolocate the material based on the moth. Unfortunately, as you can see from the image, the moth was too far gone to allow for determination beyond the level of family. And unfortunately, that family is actually widely distributed around the world. So in principle, this would have been a very good way to determine the origin of the material through this ancillary evidence, which was associated with uranium. But in this case, the decay of the moth was so great that that determination could not be made. However, the staple was a little bit more fruitful. This was discovered in the dark green powder, and it was highly corroded. The composition was consistent with high carbon iron, which is actually unusual for the manufacture of staples in Australia. So it's similar to, but distinct from the types of office staplers which you would expect to find in Australia. So again, this is also suggesting that this material and this evidence does not come from Australia. Okay, so let's recap what we've learned from this case study. So they wanted to know, the Parliament wanted to know what the chemical form of the uranium was and its isotopic composition. It was determined that the material was irradiated, depleted with uranium with an unusual, distinct isotopic composition. Number 4, determined where the uranium was mined and last chemically processed. And does it look like it came from an Australian uranium mine? Well, it seems pretty clear that these two materials don't look like the product of Australian mining. If it looks like it came from an Australian mine, could it be linked to a specific mine? But we've already determined that it looks like it doesn't come from an Australian mine. And then finally, is it related to this loss of 10 300-gram jars of yellow cake uranium from Olympic Dam, and it probably unrelated to that case. So what we're doing here, and the sort of conceptual figure you see on the left kind of shows how the more analytical techniques and the more nuclear forensic signatures we apply to a particular problem, to a particular material, the better, the more precise we can determine its origin, or conversely, we can rule out possible origins of this material. So in this case, we could rule out an origin from Australia, almost certainly. Okay, so that's the case study. I just want to conclude my remarks with talk a little bit about, if your state is interested in developing and applying the analytical techniques and approaches that you've seen in this case study, how would you go about doing that? And of course, the IEA is here to help you. So I would encourage you to take advantage of IEA training courses, workshops, and webinars in nuclear forensics. I see so many people on this particular webinar, so I know the interest is quite high. And then although your state may not have all of the analytical techniques that I described here, your state likely has some of them. Gamma spectrometry, many states have scanning electron microscopy, and the expert personnel that are actually trained to use them, even if they've never used them for a nuclear forensic application before. So what IEA training courses and workshops can help you do is apply your existing knowledge base, your existing personnel, existing analytical techniques, and learn how to use them for nuclear forensic applications. This is really important. Another thing you can do is you can participate in IEA coordinated research projects. Our CRP program is effectively an opportunity to conduct research and development projects and implement nuclear forensics capabilities through the financial support of the IEA and its donor states. We have noted that many states have been able to conduct fascinating research projects in nuclear forensics and implement key analytical techniques using the funding that's provided in coordinated research projects. So if this is something you're interested in, please reach out to me. We're always happy to include more states in CRPs. And then ensure that your technical personnel in your states are aware of and have studied IEA publications in nuclear forensics. Again, 2 notable ones include Nuclear Security Series 2G and the more recently published TechDoc 2019, which gets into a little bit more technical detail and might be a little bit more relevant for the technical personnel in your state. There's, of course, the wealth of literature that you'll find in the peer-reviewed publications, of which there are hundreds of papers on nuclear forensics. That is also an excellent resource, and I think many technical personnel know to go there to learn more about analytical techniques. And then finally, participate in capacity building activities of other partners in this area. This partnership between the IEA and UNODC is a great example. The Nuclear Forensics International Technical Working Group, in particular, their CMX series of exercises and the Galaxy Serpent virtual database exercise are excellent opportunities to get involved in nuclear forensics through a different partner. The UNICRE Prosecutor's Guide was mentioned that speaks about how nuclear forensic data can be used in criminal proceedings. And of course, there are many other resources available at your disposal, but I can't possibly cover them all. And I'm also running a bit low on time. So with that, I'd like to thank you all for your interest and your attendance, and I am happy to take any questions at this time.
Thank you, Gary, for really a fascinating presentation and case study. I'm always in awe how you're able to break down such scientific and technical terms and information into really a good understanding at the basic level, and I think our audience appreciates that as well. It's also interesting for us at UNODC to see instances where ICSANT could be applicable, provided, of course, there is a transnational element, that the requisite criminal intent can be proven, and that the material in question falls within the definition of radioactive material under ICSANT. So having said that, I do have a couple questions, and I will post the address to send questions to in case we get any. But I'll start off with one you touched a little bit during the end of the presentation on how states can share nuclear forensics expertise through international organizations. Are there any other mechanisms for states to share nuclear forensics expertise, and why is that so important?
Yeah, so thanks for that, Martin. Nuclear forensics expertise it's a really useful thing to share at sort of the regional level. We really encourage states to learn from each other about how nuclear forensics analytical techniques and methods could be implemented. One of the ways in which we can do this is through regional training courses and workshops like those offered by the IEA. In these fora, there are opportunities for states to learn from each other and to learn how states were able to identify the instrumentation necessary to perform nuclear forensics, as well as the technical personnel to give them the training and the resources necessary to perform these analytical techniques. We've definitely noticed this in our peer-to-peer workshop, which we recently launched, which really the purpose of that is to enable the partnership and the sharing of information and good practice and lessons learned between states that have maybe a more experience performing nuclear forensic analyses and states that are maybe newer on this journey. At the IEA, we really try to be a global forum for states to come together to learn from experts who've been doing this type of work for a very long time, but also for states to come together to discuss challenges as they develop nuclear forensics and see how other states have overcome these challenges. Because ultimately, the best example, I think, for states which are at the early stages of developing this capability is to see how other states have done it and to learn from them. I can talk probably for another hour about the many ways in which I've seen this happen at the IEA, but also at UNODC, ITWG, and so many other places. But I think the IEA plays a critical role here.
Thanks, Gary. I'm going to share one more question, but I encourage any questions that come through. We will do our best to answer them or share them with Gary after the event. I know we have a good mix here of both the technical side and our UNODC audience as well, more of the criminal justice officials. But this and nuclear forensics appears to be an intersection of both. What are some obstacles faced in preserving evidence in investigations involving radioactive material? So in making its way to the courtroom and into a prosecution, what are some obstacles faced there? Thanks.
Yeah, so the challenge of ensuring that not only the nuclear forensic evidence is able to be exploited in a particular case, but also the conventional forensic evidence, so fingerprints, DNA, trace fibers, and things like that. It's become increasingly apparent to the nuclear forensics community the importance of viewing this problem holistically and working together. So what we've seen and what states are really starting to do is incorporate considering the conventional forensic evidence in exercises and opportunities to practice. A really good example of this is the collaborative material exercise, which is offered by the International Technical Working Group, who have recently started to incorporate a conventional forensic component in the material that they make the subject of the exercise. So it's not just focusing on the nuclear forensic evidence, but ensuring that the conventional forensic evidence is also preserved and used, or could be used in this if there were a real case. However, I would say that the final chapter has not been written on that book, and it is challenging for states to be able to do both. So the best thing I can say is to work together with the experts, make sure that the nuclear forensics team are working closely with the conventional forensic experts to ensure that the full spectrum of information is retained, because that information is going to be important in criminal proceedings, the nuclear forensics evidence and the conventional forensic evidence.
Thank you, Gary. I see we've reached the top of the hour here, so I'll move to the closing. I'd once again like to thank you, Gary, for your time today and the informative and interesting presentation, and also to the IAEA. I would like to thank the Australian Permanent Mission to the UN and international organizations in Vienna, in particular, Ms. Marina Francis and Ms. Emma Nicholas. Gary highlighted the importance of nuclear forensics through an interesting and informative case study, and spoke of some of the key mechanisms available in gathering evidence in crimes involving nuclear or other radioactive material. I would like to thank you, the audience. I see some 80 who were with us for the hour, for their time and attention and for interacting. And lastly, again, thank you to the European Union for its financial support to UNODC, which make events like today's possible, as well as the others under this webinar series, which you can view on our ICSANT website, and for further contributions to the promotion of this convention. Please be on the lookout for information related to upcoming webinars. And with that, I will close the webinar and wish you a pleasant weekend. So thank you.